And welcome back to Mr. Cole's exciting adventures in physics. So, where we left off last time, we did a video on free body diagrams. Hopefully, you got that. Today's video is we're going back to the examples we did, and now we're going to do some teachers do this thing, they call it net force. I usually do not call it that, even though it is. You'll usually see me do this notation where we do sum of the forces. And so essentially what we're going to do is we're going to look at every single problem. Give me a little bigger writing for a second. And we are going to either do a sum of the forces X, a sum of our forces Y, or both. Again, some of your teachers will write like F net X equals, and uh, it's just, to me, it's sloppy. I don't like it. So anyway, now that I've explained myself, let's go back to the Bernie Sanders scenario where the same thing as a block setting on a surface kind of a thing. And so if that's your free body diagram, then what does your sum of the forces look like? So in the case of this one, we'll just go, wow, that's still really, really big, isn't it? Try it again. Sum too small. All right, come on. Just right. I feel like a Little Red Riding Hood here. Sum of the forces X is equal to. And so I'm doing this and I'm writing zero because, well, there are no forces on the X, but I still like to do that. So the sum of my force is now Y. I'll just look at it. And unless I've got any reason to think otherwise, I usually am going to always consider that to be positive y, and therefore this down here to be negative y. Now, if an object is moving or accelerating, I will make whichever direction it's moving positive. But in this case, I'm going to write n minus mg, and since Bernie was sitting completely static in his chair, I'll just write it's equal to zero. And that would be my sum of the forces on that one. So the net force would be equal to zero. So now we have this scenario of someone pulling a car, and it looked like this. And so here's what I'm going to do. I'm going to assume it's going to the right, so I'm going to make that positive x. This would be my negative x, positive y, negative y. So again, I usually make, anytime there's movement, I make the direction of the movement, I make that my positive x. And so this case, it worked out fine because I always make that positive x anyway. So let's do this. So play this game. Sum of the forces x is now equal to, well, here's the catch with this guy, right? You see this force, this tension is at an angle. So there's a tension x component and a tension y component. And that's why it's so important that you learn how to do vectors before you do this, because I know that my vector, my x component, is t cosine of whatever that angle is. So based on me knowing that, I'm going to say this. I've got a t cosine theta in the positive x direction, and that's it. So now I'm going to go backwards. Is there anything working against me in this problem? And yeah, I've got this friction here, so I'm going to write minus Fk. And now I'm going to write it equal to, well, this is the thing. If it said constant velocity, I'd write 0. If it said this dude was accelerating the car, then I would write ma. You just have to read it. Sum of the forces y then would be equal to. So now we're looking for anything in this problem that either points up or has a component directed up. Well, let's look at this tension. We've got a tension that's at an angle, so part of it was in the x, and then part of it's in the y, and so we'll do sine of theta for this. So t sine of theta, I'm going to write plus, because I've also got a normal force up, minus my mg, and then I'm going to set it all equal to 0. And I'll throw a little hint on you here. Whenever you're doing these, uh, I do not foresee you ever having one where there's a x acceleration and a y acceleration. So you're usually going to work these out, something of this nature. The only time you'll have like some kind of weird acceleration in an oddball direction is if your teacher is doing like resultant forces on an object, I always call them a sailboat question, something like that. Anyway, so that problem's over. Next click was the skydiver. And, I've got to do it. Sum of the forces x is equal to 0. I just like stating that. And now the sum of my forces in the y direction, this object is falling. And so I'm going to do something since it's falling. Now this is where everything gets like, you're going to be like, I'm angry with you, Mr. Cole. I'm angry. Um, Most of the time that's my positive y, I admit. And if these forces were balanced, that's exactly what I would do. But I'm going to say that maybe this is a situation where they're not. The skydiver is speeding up. I'm going to make this my positive y, and I'm going to make this my negative y direction. Because whenever something is falling in particular, especially if it's accelerating, I'm going to make the direction it moves, and you're thinking, Mr. Cole, you're making this harder. No, I'm making your life easier. So this is going to be my positive direction. So I'm going to write now mg, so that force causing it to accelerate, and I'm going to subtract that drag force away from it, and I'm going to set that equal to ma. Now, if this object was moving at constant velocity, it really wouldn't matter what you did, because in the end, all that would happen is they would end up equal to each other anyway. And so here we had the penguin on the sled. And so as we do this one, sum of the forces x, and guys, if you got this, you can quit. You may already be like, Mr. Cole, I'm totally killing this. Then you're good, guys. So the first thing I'm going to do though is this. I'm going to look at this. The sled is moving to the right, so I'm going to call that my positive x. But why is it moving? For some reason, y'all always think something had to be pushed or kicked to move. In this case, it's on a hill, so gravity is moving it. But here's the thing, that force of gravity has got two components. There's an mg component that's in my x direction, and then there's also you got it, an mg with a y component. And I have to address those components when I do my sum of the forces over here. So my sum of the forces x is this mg that's in the x. Now, I want you to look at this, because this is what will drive somebody crazy. Let's do our SOHCAHTOA. So there's my hypotenuse. The, the mgx is my opposite, and then that mgy is my adjacent side. So when I go to work this out, mgx, well, that would be mg sine of my angle would be this x component, because I want this component, again, that's in the x direction. So in order to do opposite hypotenuse, that means mgx would be equal to mg sine of my angle. And I feel like y'all get so used to always x's are cosine, x's are cosine. Well, x's is cosine if you come off the x-axis. So that's kind of one of those important things to watch. So watch this, guys. I'm going to write mg sine of theta. That addresses my positive x, minus fk. And I'm going to give you a little heads up. Friction is equal to mu k n. So a lot of times you'll see me work this problem. I'll just go ahead and write mu n in that spot. If this penguin was going down the hill at a constant velocity, we'd set it equal to 0. If the penguin is accelerating, we set it equal to ma. All I can say, guys, you just have to read your problem. Forces in the y direction, I'm going to by default always make that my positive y. And so I'm going to write n minus the y component of this mg, which in order to do that, that's my adjacent side. So that's going to be my cosine. So I'm going to write n minus mg cosine theta, and that's equal to 0. All right, guys, we are moving on at light speed. Let's take a look at the guy pushing this thing up the truck. Y'all should be able to pause this video and beat me on this. Sum of the forces X, sum of the forces Y. I'm going to do something. I'm going to make this my positive X direction because the guy is shoving it in that direction. So this would be my negative Y. Uh, it, it's moving in the plane of X. I'm going to make that positive Y, negative Y, just like typical. Sum of the force is X. So I'm going to look for my positive pushing force first. And I've got this force, so I'm going to write F minus Fk. And then this is where somebody's going to forget something. You've also got this horizontal component of the mg that we got from doing this. This is my opposite of that angle. So I'm going to write minus also, give me back red so I stay true to that, mg sine of theta, and set it equal to, we'll say ma, that this guy's winning the war. My sum of the forces y, I would just write n minus mg cosine of theta, and I'd set that one equal to 0. All right, guys, we got one left, and you can find also on my channel where I work this problem. You know what I've got to do. Sum of the forces X is 0 for this guy. Sum of the forces X is 0 for that one. I must do that. And now I'm going to do some sum of the forces Y for each one of these objects. If you want to see this solved, I've got a video where I do problems like this. So now I'm going to do something. I intentionally set this up where M2G was the larger. That means this object is falling over here, and it means this object is rising over here. And again, I always make the direction of my motion my positive direction. So like for this object, that's positive y, this is negative y. But for this object that's doing the falling over here, that would be my negative y direction, and this would be my positive y direction. And again, that makes this problem easier, I promise, if you'll always keep that in mind. So just remember this: when you're falling, your world turns upside down. Maybe that'll help you as you do this. So here we go. So sum of the forces y, I'll look at this one, my positive y. So I've got T minus M1G, and we'll assume it's accelerating, so I'll write M, not just MA, but M1A. And the physics is done for that one. Now for this other problem, I'll look at my positive y direction first, which I've got M2G minus, working against it, I've got a T because I'm falling and my world turned upside down. And now I'm going to set that equal to M2A. Mr. Cole, do I have to do it this way? You don't have to, but then you'd have to set your forces equal to negative M2A, and after 25 years, I've determined that's a harder way of teaching it. Guys, this is the easiest way of teaching. Well, I hope this finds you healthy, wealthy, and wise, and you keep on enjoying physics, and this helps you out. Till later, guys. Y'all take care. Bye.